It is probably one of the most annoying, mundane things in the world. You open a shipping box, and suddenly those little white packing peanuts are just clinging to your sweater.
Oh, yeah, your sweater, your hands, the dog, everything.
Right. And you try to brush them off, but they just, fly right back onto you. We all know it's static electricity.
Sure.
But what if I told you that the exact same mathematical machinery used to explain why those packing peanuts stick to you, well, it's actually the foundation for the most successful theory in all of human history.
It sounds like a stretch, but yeah, it's absolutely true.
I'm talking about the standard model of particle physics. It's the framework that explains almost everything in the known universe. But there is a massive, mind-bending catch here that you probably didn't see coming.
Yeah, the math holding all of this together, physicists and philosophers cannot even agree if it actually exists in the real world.
Which is just wild to me.
It is a staggering paradox when you really look at it. I mean,
Right.
we have this incredibly precise description of reality, yet at its very core is a mathematical entity that might just be a figment of our collective imagination, like a mere tool we invented.
And that is exactly our mission today.
Yeah.
We are doing a deep dive into the Stanford Encyclopedia of Philosophy's entry on gauge theories in physics.
It's a great source for this.
It really is. We want to look under the hood of reality today and ask, are the mathematical quantities that describe our universe physical realities, or are they just human scaffolding?
So to get there, we really have to start with this concept of a gauge potential.
Okay, let's unpack this. Let's use the packing peanuts.
Perfect. So the theory of electrostatics uses an electrostatic potential to explain the force that's pulling that peanut to your sleeve.
Right.
It basically assigns a value of energy to every single point in space around you.
So think of it like an invisible three-dimensional grid filling the room.
Exactly, yeah. And every point on that grid has a specific number attached to it. That number is the scalar potential.
Okay, so it's just a magnitude, like a single value.
Yeah, kind of like how a thermometer tells you the temperature at one specific spot in the room. If the peanut is sitting in a spot with a high potential, it gets pulled toward a lower potential.
Which happens to be your sweater in this case.
Right.
So that sounds pretty straightforward, honestly. It feels tangible, like temperature or air pressure. So it makes me wonder how we ever got to a place where physicists started doubting the very math they invented to describe this.
Well, the doubt crept in because the math started allowing for situations that just didn't make any physical sense.
How so?
This goes all the way back to the 19th century with the pioneers of electrodynamics, particularly James Clerk Maxwell.
Oh, sure. Maxwell's equations.
Right. He formalized this idea of the potential, but he also noticed a glaring issue. And it is beautifully illustrated by something called Faraday's cube.
Okay, what is that?
Imagine a hollow metallic vessel, essentially a giant metal box. You put a few objects inside it, close it up, and then you heavily charge the outside of the box with electricity.
Okay, I'm picturing like a metal safe getting zapped with a huge Tesla coil.
That's a great mental image. So mathematically, if you look at the equations for the scalar potential, the values on that invisible grid inside the box rise and fall drastically as you charge and discharge the outer surface.
So the math is saying the internal state of the box is changing.
Yes. But physically, absolutely nothing happens to the objects inside.
Wait, nothing at all.
Not a thing.
Which completely violates our basic intuition about how the physical world works. I mean, if I put something in a metal box and hold a blowtorch to the outside, the temperature inside goes up.
Right. And the object melts.
Yeah, temperature is a real physical property, so changing it causes a physical effect.
Exactly.
But with this electrical potential, the numbers on a grid skyrocket, and the objects inside don't even flutter.
And that observation forces a profound philosophical question. If a mathematical quantity changes wildly, but empirical reality doesn't change at all, is that mathematical quantity a real thing?
I mean, Maxwell himself decided it wasn't.
Right. He did. He called the electrostatic potential a mere scientific concept, arguing we have zero reason to regard it as a true physical state.
Wow.
Yeah, and over time, philosophers actually formalized this debate into three distinct camps regarding how we should interpret these potentials.
Okay, let's go through those.
The first is the significant interpretation. This camp argues that the potential is, in fact, a real feature of the world, and if we strip it out of our theories, we are ignoring a fundamental piece of reality.
Even if we can't directly observe it doing anything in that Faraday box.
Correct. Now, the second camp is the surplus interpretation. They view the potential as real, but entirely redundant.
Redundant how?
Like it's a byproduct of how we write the theory, not something that actually drives physical events.
Oh, I see.
And finally, there is the scaffolding interpretation. This is the strictest view, arguing the potential is strictly a mathematical tool. It makes zero actual contribution to the physical content of the universe.
I love that scaffolding analogy, honestly. It perfectly captures how we build things.
It does, yeah.
Because you absolutely need the metal scaffolding to construct a skyscraper. You need it to hold the beams, to let the workers reach the roof.
All right.
But once the building is finished, you tear the scaffolding down. You'd be crazy to look at the finished skyscraper and say the scaffolding is part of the architecture.
Exactly. And late 19th century physicists literally tried to tear the scaffolding down.
They did.
They did, quite aggressively. Physicists like Oliver Heaviside and Heinrich Hertz took Maxwell's work and reformulated it specifically to eliminate these potentials.
Just get rid of them entirely.
Right, because at this point, the math had evolved from just a scalar potential, a single number, to include a vector potential.
Okay, what's the difference?
A vector potential is a number that also has a direction, like wind speed blowing north. Heaviside and Hertz absolutely hated this vector potential.
Really hated it.
Oh, yeah. There's a famous quote where they boast about murdering it, calling it that wonderful three-legged monster with a scalar parasite on its back.
Physicist trash talk is truly unmatched. A scalar parasite. I love that.
It's pretty brutal, and they were victorious for a while, too. They managed to rewrite the entire theory of electromagnetism using only the observable, measurable electric and magnetic fields.
So they banished the potential.
Completely. The scaffolding camp seemed to have won definitively.
Oh.
The monster was dead, and physics was cleaner for it.
But here's the thing. If Heaviside and Hertz so thoroughly killed this mathematical monster, how did we end up with it haunting modern physics?
That's the million-dollar question.
Because obviously it didn't stay dead. The universe, or at least quantum mechanics, simply refused to let it go.
Here's where it gets really interesting. The resurrection happened in 1959 with a theoretical proposal known as the Aharonov-Bohm effect.
Okay.
It completely shattered the idea that potentials were just scaffolding. Aharonov and Bohm took the famous double-slit experiment.
Where you shoot charged particles like electrons at a screen with two tiny slits to see them behave like waves.
Exactly. But they added a massive complication to it.
Because normally, in a double-slit setup, the electrons just pass through empty space, go through the slits, and hit a detector screen, creating a striped interference pattern.
Right.
So I'm guessing they put a roadblock in that empty space.
They did. They proposed placing an infinitely long, perfectly shielded electromagnet, a solenoid right down the middle, between the two paths the electrons take.
Okay.
The critical detail here is perfectly shielded. Outside that solenoid, the measurable magnetic field is absolute zero.
Got it.
The electrons flying by never experience any magnetic force pushing or pulling them. So according to the classical physics of Heaviside and Hertz, changing the magnetic field trapped inside that shielded tube should have absolutely zero effect on the electrons outside.
Right, because the force is zero. The observable field is zero. It's basically Faraday's cube all over again.
But quantum mechanics operates on different rules. Aharonov and Bohm's math predicted that if you change the electrical current inside that heavily shielded solenoid, the striped interference pattern of the electrons on the distant detector screen will physically shift. Yeah, the peaks and valleys of the electron wave get knocked out of sync. And when experimentalists actually built the setup in the 1960s, the prediction was flawlessly confirmed.
Okay, I have to pause here, because this sounds completely illogical.
It does.
How can an electron flying through a vacuum alter its path based on a magnetic field it never touches and mathematically cannot feel? Is this just magic? It sounds like spooky action at a distance.
And that was the exact dilemma the legendary physicist Richard Feynman wrestled with.
Oh, really?
Yeah. What's fascinating here is Feynman concluded that there was only one way to avoid accepting spooky action at a distance.
Which is the absurd idea that a magnet can instantaneously affect an electron across a barrier with nothing connecting them.
Exactly. So to avoid that, we are forced to admit that the vector potential, the murdered monster, is physically real.
Okay, so the magnetic field is trapped inside the shield, but the mathematical potential, that invisible grid of values, spills out into the room. It permeates the space where the electrons are flying, and the electrons interact with the potential.
That is the only logical conclusion. The potential carries physical information about the magnetic field into the surrounding space. So the significant camp suddenly had an experimental smoking gun.
The potential had to be real.
It had to be. However, the Stanford Encyclopedia points out that bringing the potential back to life introduces a terrifying new philosophical problem. It is called holism, or non-separability.
Holism. Let me see if I can unpack that. Usually, we assume that if you understand all the tiny individual pieces of a space,
Yeah.
you automatically understand the whole space.
Right.
Like if I know everything about every brick in a wall, I know everything about the wall.
That is the principle of separability, and it has been the bedrock of science for centuries. But the Aharonov Bohm effect destroys it.
How so?
Well, you can look at the electron's path on the left side of the shield, and the magnetic field is 0. You look at the path on the right side, 0. But when you look at the entire loop, the whole region encircling the solenoid, the physical state suddenly depends on the magnetic field trapped inside.
It's like looking at two completely blank puzzle pieces. But the second you snap them together, a vibrant picture suddenly appears out of nowhere.
That's a great way to put it.
The whole system possesses physical properties that are completely absent from its individual parts. That breaks our fundamental logic of cause and effect.
It really does. It forces us to accept that reality might be deeply non-local, but this holism is just the beginning of the headache, honestly.
Oh, there's more.
Yeah, the properties of the potential itself tell us that our understanding of time and causality might be broken too.
Wait, time and causality.
Because if we accept that these gauge potentials are real physical things in the world, we run face first into the nightmare of indeterminism.
Okay, let's clearly define what we mean by indeterminism here. In classical physics, the universe is like a giant clockwork mechanism, right? If I know the exact position and momentum of every gear right now, and I know the laws of physics, I could predict with absolute certainty what the clock will look like tomorrow. The present strictly determines the future.
But gauge theories have a built-in mathematical flexibility called gauge invariance.
Which means what, exactly?
This means you can wildly change the mathematical value of the potential, and it will have absolutely zero effect on any observable physical outcome.
Okay.
The source material highlights a massive problem this causes, specifically looking at two different mathematical rules, known as the Coulomb gauge and the Lorentz gauge.
And these aren't just minor rounding errors, right? They're entirely different sets of instructions for calculating the potential.
Yes, completely different. You can use Coulomb's rule, or you can use Lorentz's rule. Both are perfectly valid under the laws of physics. But here's the crisis. If you pick one rule, it dictates a specific value for the potential today, which mathematically guarantees a specific different value for the potential tomorrow.
Right.
If you pick the other rule, you get a completely different mathematical future. There are infinitely many mathematical rules you could invent, leading to infinitely many different physical futures.
Let me try to visualize this.
Yeah.
It's like standing at an intersection, and your map app generates infinite, equally valid routes to your destination.
Exactly.
You hit start, and your car magically drives to the destination.
Yeah.
But if you ask the app, which of these infinite physical roads did my car actually drive on, the app completely refuses to tell you.
Yes.
Worse, the laws of physics themselves refuse to tell you. Every single route perfectly explains how you arrived.
That is a perfect analogy. The laws of electromagnetism simply do not determine which future evolution of the potential is the true one. If the potential is a real physical feature of the world, then the universe itself is profoundly undecided about its own future state. Yet, from our human perspective, observing the electric and magnetic forces, the world looks perfectly deterministic and normal.
So what does this all mean? How do we deal with a theory where the physical future is infinitely undetermined? Do we just accept that the universe is broken?
Well, most philosophers argue that if a theory suggests radical indeterminism for invisible things, while the visible world ticks along like a clock, we've probably made a massive interpretive mistake.
So we took a wrong turn somewhere.
Right. It strongly suggests we need to abandon the significant camp and retreat back to the surplus or scaffolding views.
Okay, so the infinite roads on your map app aren't real physical roads. They're just a redundancy in the app's software code.
Exactly. It's descriptive fluff.
Descriptive fluff. But faced with this indeterminism, where the math spits out infinite possible realities, you'd think physicists would just throw their hands up and abandon the whole framework.
You would think so.
Instead, they did the exact opposite. They weaponized this ambiguity. They turned it into the ultimate cheat code for discovering the universe.
Yeah, this is where we meet the gauge principle.
Okay.
It started with the mathematician Hermann Weyl in 1918. He had a theory about the conventions of measuring length and general relativity that didn't quite pan out.
Right.
But 10 years later, he repurposed the core idea for the quantum mechanics of charged particles, and Weil realized something astonishing.
What was it?
If you take the equations of quantum mechanics and you demand that they remain balanced even when you arbitrarily shift this invisible gauge potential at different points in space, the equations fight back.
Wait, what do you mean they fight back?
To keep the math from breaking under this arbitrary shift, you are mathematically forced to introduce a new field to compensate.
Okay.
And that compensating field turns out to be the exact equations for the electromagnetic field.
Wait, let me make sure I am following this.
Sure.
By demanding that the math scaffolding stays flexible, by insisting that our descriptive fluff can be shifted around without breaking the final answer, the actual physical force of electromagnetism just pops out of the math as a necessary side effect.
Yes. The math dictates the physics. And in 1954, physicists Chen-Ning Yang and Robert Mills realized the sheer power of this.
What did they do?
They asked a brilliant question: what if we make the scaffolding even more flexible? Instead of just shifting an invisible value, what if the math has to remain perfectly identical if we arbitrarily swap the labels of the particles themselves?
So saying a proton is a neutron and a neutron is a proton, just swapping their identities in the equation.
Exactly. It's called isospin symmetry. If you demand that the universe operates exactly the same way, regardless of whether you call a particle a proton or a neutron, the pure math breaks. Unless you invent a new, highly complex field to act as a universal compensator for that swap. When Yang and Mills derived the math for that compensating field, they accidentally gave birth to the exact mathematical structures needed to describe the strong and weak nuclear forces.
It's like trying to change the rules of a game mid-play. If you suddenly decree that a pawn can move like a queen, the game breaks.
Right.
The only way to keep the game fair and playable is to introduce a complex new handicap system.
Yeah.
And in physics, that handicap system manifests as a fundamental force of nature.
That's spot on.
You demand symmetry, and the fundamental forces are handed to you on a silver platter.
And this incredible trick of nature is deeply rooted in Emmy Noether's famous 1918 theorem. Noether proved one of the most beautiful and profound ideas in all of science.
Okay, wait a minute.
She showed that every continuous mathematical symmetry in nature corresponds directly to a conserved physical quantity.
Now, by continuous symmetry, we mean something you can shift smoothly, like rotating a perfect circle. No matter how much you turn it, it always looks exactly the same.
Precisely. Noether proved that the gauge symmetry of electromagnetism isn't just an abstract mathematical game. It is the exact reason why electric charge is conserved in the universe.
Oh.
The fact that the total charge of the universe never changes, that you can't create or destroy charge out of nothing, is intrinsically linked to this mathematical flexibility.
The sheer irony here is just staggering. We established earlier that this gauge potential might just be scaffolding, a human invention that philosophers say isn't even real.
Right.
Yet, physicists use the flexibility of that exact scaffolding to build the standard model of particle physics. And they didn't just use it to discover forces, they used it to fix theories that were completely broken.
That was the monumental achievement of Martinus Veltman and Gerardus 't Hooft. Early versions of these Yang-Mills theories were a disaster, honestly.
Really? How bad?
When physicists tried to calculate the probabilities of certain particles interacting, the answers would come out as infinity. Or they would get probabilities that added up to less than 100%, which is physical nonsense.
Right, you can't have a 120% chance of an electron existing or a negative 20% chance. That's absurd.
But Veltman and 't Hooft proved that you could use the flexibility of gauge invariance, the fact that you can shift the scaffolding around without changing the physical outcome, to selectively cancel out those infinities.
Oh, that is clever.
The descriptive fluff was the cure to the mathematical garbage. By choosing the right gauge, the absurdities vanished, leaving behind the precise functional standard model we use today.
But if the scaffolding is fundamentally just mathematical flexibility, a clever way to balance equations and cancel out infinities, we hit an absolute brick wall when we talk about creating actual physical stuff.
You're talking about mass.
I am talking about the origin of mass.
Yeah, you are pointing directly at the massive philosophical tensions surrounding the Higgs mechanism.
Right.
In our universe, the particles that carry the weak nuclear force, the W and Z bosons, are incredibly heavy. But the pure, beautiful gauge math we just talked about demands that they must be completely massless, like photons of light.
And if they have mass.
The equations break and the infinities return.
So how does the theory fix that?
It uses something called spontaneous symmetry breaking. The textbook explanation asks you to imagine a perfectly symmetrical system. Think of a pencil perfectly balanced on its tip.
Okay.
It is completely symmetrical, equally likely to fall in any 360-degree direction, but it is incredibly unstable. The moment it falls, it picks a specific direction. The perfect symmetry is spontaneously broken.
So the universe started out like that balanced pencil with massless particles and perfect symmetry. But then the pencil fell.
Yes. The universe is filled with a Higgs field. When the gauge symmetry of the early universe spontaneously broke, the gauge potentials were forced to interact with this field.
Okay.
Through a complex mathematical reshuffling of the equations around this broken symmetry, a particle that was mathematically massless suddenly absorbed components of the field and gains physical mass. And a new particle, the Higgs boson, appears as a byproduct.
And here is the ultimate pushback. Let's go back to the philosophers.
Let's do it.
If we accept the scaffolding view, if we agree with Maxwell that a gauge transformation is just a change in our human mathematical description, like switching a blueprint from inches to centimeters, how can a particle gain actual heavy physical mass from a mathematical reshuffling? You can't weigh math.
It is a devastating objection. The philosopher John Ehrman summed up the absurdity perfectly. He wrote, "Neither mass nor any other genuine attribute can be gained by eating descriptive fluff."
Eating descriptive fluff. That is brilliant. If the scaffolding isn't real, if it's just software code, it cannot miraculously forge a heavy iron anvil.
Exactly. If the Higgs mechanism is merely a reshuffling of variables, a change of human description, it cannot be a literal physical process that creates mass.
Right.
Yet the W and Z bosons undeniably have mass. And the Higgs boson isn't just math. It was physically detected in the Large Hadron Collider at CERN in 2012. There has to be genuine physical content there.
So the physics works flawlessly, but the philosophical explanation of why it works is entirely broken.
That's the current state of the field. This contradiction forces physicists and philosophers to constantly search for gauge-invariant explanations of the Higgs mechanism.
What does that mean in practice?
They're trying to rewrite the theory using only quantities that do not depend on the descriptive fluff. They want to find out what is genuinely happening at the physical level to create mass without relying on an illusion of mathematical symmetry breaking.
Wow. Let's take a breath and synthesize this incredible journey.
It's a lot to take in.
We started with a simple static cling of packing peanuts.
Huh?
That led us to Maxwell's invisible scalar potential and the mystery of Faraday's cube, where changing the math did absolutely nothing to the objects inside.
Right.
Then, quantum mechanics and the Aharonov Bohm effect brought the murdered potential back to life, proving that hidden math actually does shift the physical path of electrons.
But resurrecting the math broke determinism, giving us a map app with infinite possible futures. Physicists then took that indeterminism and weaponized it as the gauge principle, demanding mathematical symmetry to miraculously discover the nuclear forces.
And finally, we slam into the Higgs mechanism, where we're still trying to figure out how the universe manages to eat descriptive fluff to create the heavy building blocks of reality.
Yeah.
It proves that physics isn't just about plugging numbers into equations to get an answer. It's about the exhausting, centuries-long debate over what those numbers actually mean.
And if we connect this to the bigger picture, the source material leaves us with a truly staggering thought.
Yeah.
Philosophers like Arnsenius, Below, and Maudlin suggest that grappling with these gauge theories might require a deep metaphysical revision of reality itself.
How deep are we talking?
Well, from the time we are infants, we are taught to view the universe as a giant container filled with independent, isolated objects. A ball, a chair, an electron, each holding its own inherent properties.
Right. Things exist independently. A brick is a brick, even if it's the only thing in the universe.
But what if that is fundamentally wrong? Because of the extreme holistic nature of gauge theories, remember the Aharonov-Bohm effect, where the whole loop dictates properties that the individual pieces lack? These philosophers propose that the foundation of reality isn't made of objects at all.
What is it made of then?
What if the universe is primarily constructed of relational loop-like structures and overlapping fields of potential? What if the distinct objects we think we see are just localized illusions, mere byproducts of how the mathematical scaffolding interacts with itself?
Oh, man. That is going to keep me up at night. The idea that independence is an illusion and the connections are the only things that are real.
It's a massive paradigm shift.
It really is.
Mm-hmm.
So the next time you open a shipping box and those packing peanuts fly out and stubbornly stick to your clothes, take a close look at them.
Yeah, look closely.
You might be looking at independent objects bound by invisible static forces. Or you might just be looking at the illusions of a loop-like universe wrapped in the mysterious, shifting scaffolding of the gauge potential. Something to chew on. Thanks for joining us on this deep dive.